Hey crew, I decided to go ahead and do 4.2 as a video. That way tomorrow, which is going to be Thursday, will actually be a day we can spend maybe reviewing the tests a little bit or answering questions for test 1. Remember, Friday we're planning on taking the retake on test 1. And then I would like this one done by next Tuesday. We don't have school at Mineola on Monday the 10th, and so this needs to be done in your homework. So section 4.1 and 4.2 need to be done by Tuesday when we come back. So we're going to do a couple of different things. Today is going to be the addition rule, and also we're going to talk about the multiplication rule when it comes to probabilities. Okay, and so in the addition rule, okay, we're going to find out that we're looking for a probability that either A or B will occur, and that the word "or" will be we'll associate that with the addition rule. We're also going to be looking at the multiplication rule, and in this case, the probability we're thinking that the event A and the event B will happen, and this would indicate that we're going to multiply. And so, anytime you think of the word "and," we're going to apply that multiplication rule. Okay, the compound event is meaning that you have two or more things that are events that are occurring at the same time. So, probability that A or B, a probability of in any single trial, an event that occurs, or event that B occurs, or that they both occur. When finding the probability of event A or B occurs, the total number of ways that A can occur and the number of ways B can occur, find that the total is such the way no outcome is accounted for more than once. So what I mean by that, really to me, let me even highlight that real quick. What they're talking about is that if we have, for instance, like say we have a deck of cards, and so we have the of a standard 52 deck of cards where you have the hearts, the diamonds, the spades, and the clubs, and say that we wanted just the probability of getting a queen, or we wanted the probability of getting maybe a heart. Okay. In this case, then, you know that there are two cards that are queens that are also hearts, and so that's what they're referring to. That we're going to only be dealing right now with cases in which there aren't combinations between the two. In other words, it can only happen once. In other words, if we did something like the probability of a queen or maybe the probability of a king, then there's no difference, there's no combination. But in this case, this is one we won't have today, but this is a case where we know that we have two cards that are both queen hearts, and so you'd have to eliminate those from your possibilities. Okay. The formal addition for that would be we would find the probability of the first one, say the probability of the queen, plus the probability of getting the heart, and then we would subtract down the probability of A and B, which would be the two cards that we have for the queen of hearts. Whoops, queen, I guess it would be just one. I'm sorry. I'm thinking of a red card, so there'd be one queen of hearts. There'd be only one of them. So, but that's the idea of what we're doing that behind. Okay. On the second page, we also have some Venn diagrams indicating the multiply, exclusive, and also the addition rule. So if you look at the first one, it says the events A and B are disjointed, or in other words, multiply exclusive if they can occur at the same time. Okay, so the example for disjointed events. So for instance, at the event A, maybe be randomly selecting from a clinical trial someone who is male, and B would be randomly selecting someone from a clinical trial who is female, and the selected person cannot be both. And so in this case, this one didn't show up very well, but B is another circle here, and this one would be, we would have to fill it in. So B then the abilities two do not occur together. We could have some that are connected, and this would be where my probability of A and B. So in other words, this is my probability of my queens, this is my probability of getting my hearts, and then this would be the queen of hearts in between. Summary. The summary of the key points we had, again, remember we're going to have values of P which is the probability of A or B occurring, and that we're going to associate or with then addition. And then to find the probability of A or B, we are going to add those two events. Okay, the complementary events is such as the addition rule. We're going to have that probability of A and probability of A are disjointed. And then the rules of the complementary events is that the probability of A plus the probability of A again would be equal to 1. So, the second page, your page, was set, these two are also, the probability of not getting an A would be 1 minus the probability of A, and the probability of A would be also be 1 minus the probability of not getting an A. So with that, let's go ahead and just start working with some of the multiplication rules. So again, the word and is going to be associated with the word with multiplication. And so in this case, the probability of A and B represents the events that occur with A in the first trial and B, the events B occurring in the second trial. Okay, the probability of B/A represents the probability of B occurring after an event A has already occurred. And then you would also have the probability of A and B, so the probability of A times the probability of A. So, a couple of things that you'll need to know will be independent and dependent. If two events are independent, or if they are going to, the occurrence of one does not affect the probability of the occurrence of the other. So, several events that are similar independent to the occurrence of any does not affect the probabilities of the occurrence happening to the other. If A and B are not independent, then they're also then dependent. And so a dependent occurrence would be the ones that affect the probability of the occurrence of the other one. But this does not necessarily mean that one of the events is the cause of the other one. So a little diagram to kind of help us with understanding this occurs here on the next page. So if you start, we have the probability of A and B would be the multiplication rule, and then you would have to decide, is it going to be, are the events of A and B independent? If yes, then you're going to use this formula where the probability of A and B equals the probability of A times the probability of B. Be sure that if you would answer no, that they're independent, be sure that the probability of the event B by assuming the event A has already occurred. So we're going to work a few problems so that you kind of can understand some of those. So the caution, some cautions that we do for the rule of one. And generally, when the probability of any sequence or independent events is simply the product of their corresponding probabilities. Remember, sampling. Sampling is going to be in the world of statistics, sampling is the methods that are critically important, and the following relationships will hold: sampling with replacement, and with independent events, and then sampling replacement with dependent events. So we'll talk about those. When sampling without replacement, the same sample size that is no more than 5% of the size of the population will treat the selections as independent, even though they're actually dependent. So you might go ahead and think about this, highlight this 5%, and then if they're the sample size is less than 5%, then we're going to treat them as independent. In other words, that we really don't even have to worry about whether or not we're going to pull them out or not. And I noticed, what's with my filter? Okay. So let's assume this example. Assume that 3 adults are randomly selected without replacement. Okay, so in other words, we're not pulling them out from the 247,436,830 adults in the United States. Assume that 10% of those adults in the United States use drugs. Find the probability that the 3 selected adults all use drugs. So in this case, we're going to be looking for then, okay, because of the fact that the 3 adults are randomly selected without replacement, all 3 events are dependent, okay, and we can then treat them as independent by applying the five guideline for cumbersome calculations. And when you think about, if you think about the 5%, so in other words, if I take the 247 million times that 0.05%, that would be the number that I could pull out, and clearly 3 is going to be less than that. If we get, in this case, so if we're wanting to get the probability that all 3 adults use drugs, and we know that that is going to be then 10%. So to find the probability that we have 3 adults on this, we would take then the probability of the first one uses drugs. It'll be then times, and so we need to add put a little time sign between, times the second one that uses drugs, times the third one that uses drugs. In other words, it's going to be 0.10 times 0.10 times 0.10, which then would be then 0.001. So there is a 0.001 probability that all 3 selected adults use drugs. Can I ask you, I want you to look right here, why did we put the 2 zeros behind? If you think about it, we had to go 3 significant digits, and it's usually follows behind. So that's, again, another idea on why we have to do those extra zeros, even though that they don't affect the number that we have. Now, redundancy, the principle of redundancy is used to increase the reliability of many systems. Our eyes have passive redundancy in the sense that if one of them fails, we continue to see. An important finding in modern biology is that the genes of an organism can often work in place of each other. Engineers often design redundant components so that the whole system will not fail because of failure of a single component. So what happens is, what they're saying is that take airplanes, and what we're going to talk about, you're going to have multiple systems so that if one happens to fail, you have to and that will also increase your probability. This one kind of makes sense when I start on with the examples. So assume that a typical flight, the probability of the hydraulic system failure is 0.002. So this is a key part. If the Airbus 300 were to have one hydraulic system, then the probability that the aircraft's flight control would work for a flight, or what would the probability be for that? Well, in this case, then you would have then the probability of a failure would be then the point. Let's see. So what was the probability that the flight control would work for a flight? So this is the part that is going to be a failure. So we know that the probability, the P, of it working would actually be the probability of not. Let's do a not and then a fail. Okay, in other words, that would be the same as 1 minus then 0.002 or then 0.998. Okay, given that the Airbus actually has 3 components, 3 independent hydraulic systems, what is the probability that on a typical flight control can be maintained without a working hydraulic system? And so in other words, we're talking about how much of that would fail. So we're looking for probability that all 3 fail. And if that's the case, if one fails, it's going to be 0.002. Then the next one would be the multiplication of that, so I'm going to take it times 0.002. And then also the next one, the third one, would be 0.002, which is the same thing, remember, as 0.002 and then all to the third power. Okay, in this case, then the answer for the probability that all 3 would fail would be then I have 1, 2, 3, 4, 5, 6 zeros, and then I would have 2 to the third, which would be 8, which is a very, very small number. So In this case, the solution would be listed there below. And then you have the example here. So what is the probability, this probability that it does not happen, that all three systems fail? Remember, that's where we take the probability of it 1 minus that amount. And so the probability that it will that you will end up flying and at least one of the hydraulic systems will work is going to be then 99.99992%. Okay, so let's go ahead and look at the summary rule with the addition rule and then also the multiplication rule. So remember, again, just a reminder, if we have the or, with probability that two events or one event or another event happens, that suggests addition. If we have the word and, that's going to suggest the multiplication. So let's look at some example problems. Okay, so the first one is going to be that we have 15,500,971 adults in Florida, and if the Gallup organization randomly selected 1,068 adults without replacement, so another key part, are the selections independent or dependent? And if the selects are dependent, can they be treated as being independent for the purposes of any of the calculations? So the question is, what you need to look at is, we're looking at what percent is the 15,524,971. If we were to think about it, we're saying what is 5% of that population, if it's less than 5% of that population size. So in this case, this is going to be a dependent. D-E-P-E-N-D-E-N-T. And it can be considered independent for the purpose of the calculations since we have such a large sample size. So it can be independent because of the large sample size. The next example, a U.S. cellular survey of smartphones showed that the 26% of the respondents answered yes when asked if abbreviations such as LOL are annoying when they're texting. I think these are probably the older Americans would be my guess, but what is the probability of randomly selecting a smartphone user and getting a response other than yes? And so in this case, since the probability we're looking for of not yes, okay, if we have the probability of yes is going to equal the 26%, or remember we're going to 0.26, then the probability of not getting yes would be the opposite, so it would be 1 minus the 0.26. And that then in the case then is going to be 0.74 or 74%. Now on the next example, it says the data in the following table, which lists the drive-through order accuracy at the popular fast food chains. And so assume that the orders are randomly selected from those that are included in the table. So again, for McDonald's, you have a total. Remember that as a column goes, if I have 329 that are not accurate and 33 that were not accurate, that means I had a total of 362 orders from McDonald's. And then it goes the same thing with Burger King, with Wendy's, and with Taco Bell. Now remember, if we wanted to find out how many total orders of all of 4 of the chains happen to be accurate, then we would actually add then the 329, the 264, the 249, and the 145 to get the 987. And the same thing goes with not accurate. And then we know that the total number in our sample would be then 1,118. So let's do this one. If the order is selected, find the probability of getting food that is not from McDonald's. Okay, so if one order is selected, find the probability of getting food that is not from McDonald's. And so when we look at this, we have then the McDonald's here, we know the probability of getting food from McDonald's would be then let's go getting food from McDonald's. So the little m would be then the 362, which is our total sample for McDonald's, over our total population, which is 1,118. But they ask us find the probability that it's not from McDonald's. So now all we have to do, since I'm looking for the probability of not M, then I would know that I need to just go 1 minus 362 over 1,118. And by calculating that, which I didn't have my calculator, but I kind of worked them out beforehand, so you can double check my work, I ended up earlier getting 0676. Maybe I can find my calculator. Okay, the next one, if the order is selected, find the probability of getting food from McDonald's or an order that is accurate. And so in these events are selected are the events of selecting an order from McDonald's and selecting an accurate order disjointed events. So in this case, we're looking for the probability of getting food from McDonald's or that it's accurate. Okay, so in this case, the probability of getting food from McDonald's, remember, is going to be the same 362 over the 1,118. But remember, or will tell me that I'm going to add. So I'm going to I will add this amount then. And then I'm going to go just those that are accurate. So the accurate ones I'm going to go across, and I'm going to find out that it's going to be the 987 over then the 1,118. Okay, and in this case then I also want, because I have the fact I have some events that in McDonald's that will, because this 987 included 325 from McDonald's that were accurate. That means I have to subtract out then the probability of the McDonald's and were accurate. So I'm going to subtract then 329 out of 987. And so this will be a total of, when I did my calculation, I'll have 1,020 over 118, which would be then 0.912. And again, you can double check my work, see if I added everything correctly, but that's what I had earlier. Okay, so now the next one, they ask also, is this going to be disjoint events? So in this case, when we think that the events are not just disjoint, since it is an or, then we're also going to add. Okay, and then we also have to make sure we subtract back. Don't forget that on these, it's so easy to me to start on just the probability of McDonald's, the probability of accurate, but when they're separate like that, we have to make sure that we don't have an overlap, and you have to subtract those out. C, if we have two orders that are selected with replacement, okay, find the probability that they both are going to be from Taco Bell. And are these an independent? So the very first one, so we're going to look for the probability that they're both from Taco Bell. And that means that we have the probability of both of Taco Bell and Taco Bell. And so when we look at this one, the and is going to indicate that we are going to multiply those together. And there are going to be with replacement. So in other words, we don't have to worry about subtracting that out. Now in this case, we're going to look at the probability that we have something from Taco Bell, and the Taco Bell here and our tacos are going to be 158. So I'll have the 158 over the 1,118. But then I'm going to have to multiply that again. Now, on this one, on C, with it being replaced, I'm going to keep then the 158 over 118. And so when I multiply these two together, I'm going to end up with then approximately, and divide, 0.01997, which is just approximately, remember we're going to about three digits, so it's going to be 0.01 or 20. Approximately, maybe put the little thing. Now, the change on the next one is going to be that this is without replacement. And so remember, if I have an order that I'm pulling out and it happens to be Taco Bell, then that changed my sample size a little bit. So in this case, that on this one, I'm gonna do the probability that it's still going to be Taco Bell and Taco Bell. But I know without replacement, I'm going to have to change something. So in this case, my first one is still going to be my first sample. I'm going to have 158 over 1,118. But I'm going to hold on to that one, and I'm going to have a new set. I'm going to have one less in each one. So in other words, I'm going to have one less Taco Bell order, 157. I'm going to have one less in my sample size. And so I'm going to this to the 1,117 instead of 18. And then I will also multiply those together too. And when I do, I'm going to find out that they are both, it comes out to be 0.01986, which is again approximately to three places, 0.020. In this case, okay, so the difference between independent are the events on the first one independent, and on C that they are independent because they both are equivalent to the and but the second one the events are not independent, and both are equivalent, so we will add. But we know that the first, we find the probability of getting the first order, and then the second event, now there's going to be one less, so we're going to have to multiply. We're going to have to change our fractions. So this one would be then not independent. And our last one will be E. Well, no, I guess E and F. If an order is selected, find the probability of getting an order from Burger King or Taco Bell, or if the order is going to be accurate or not. So let's go ahead and we're going to start off with, we're going to go the probability of getting Burger King. We're going to go plus then the probability of getting then Taco Bell. We have then plus the probability of getting an order from Taco Bell or that the order is accurate. So in this one that we have that the probability of McDonald's and accurate. Plus the probability of Wendy's and accurate. Because after that, if I look at my probability of getting a Burger King, that's going to include then those that are already accurate. If I have the probability of getting a Taco Bell, going to be both accurate and not accurate. And so then I want to add in just the ones that are accurate for my other two amounts, because those would be the ones that fall into the second category here, whether it's accurate or not. And that's why I'm going to eliminate then the probability of, I wouldn't do just a probability of accurate because I need to eliminate the Burger King and the Taco Bell. So then my answers are going to be my probability of Burger King, remember. I wish it was on the same page, sorry. So what I'm going to do is look through here, so it's going to be the 318. Then I'm going to go with my probability of getting, when was it, McDonald's? Oh, Taco Bell. So I'll have Taco Bell as 158. But then I'm going to also do McDonald's and accurate. So on this one, I'm going to go back to my chart. McDonald's and accurate would be then, I would have then, so McDonald's and accurate would be then the 329. And then the last one would be Wendy's and accurate, which would be the 249, and not use the total amounts. So with that, I would add up all of those amounts. So I'd have the 318 over the 1,118 plus I'm going to have the 158 divided by the 1,118 plus then the 329 over the 1,118 plus my last one, which would be the 249 over the 1,118, and that's going to equal then 1,054, and you can again check my math and pause it if you want, over 1,118, which should be approximately 0.0943. Okay, case, these events are not disjoint, and so that's why we will add them, because there's also, remember, there's going to be an or. We're going to get since the or would indicate that we would add. On F, we have if 3 different orders are selected, find the probability that they are not all accurate. Okay, so again, we're going to look for the probability that all 3 are not accurate. Okay, so if that's the case, then we're going to look at the probability of not accurate. So it's going to be the probability of not accurate. Let me just go an accurate with a line. We're going to have then and accurate, not accurate, and accurate, not accurate. So the and is going to indicate we were going to multiply. So let's go back and find out the first one. What is the probability that we have that are not accurate? So if you look at this, it's all the orders. And so I'm going to be looking at the 131. It's going to be not accurate. Now in this case, I'm going to start off with my probability with 131 over then my total population, which is 1,118. But in this case, if 3 orders are selected and the probability is accurate, we kind of need to figure out the replacement or not replacement. So in this case, we're going to assume that they're not going to be that there's no replacement. So then, in other words, we're going to find them, we're going to hold on to them, and so that's going to change then my sample size. So if I have one I've held out, then I'm going to have to reduce this to 130, and I'm also going to have to reduce my population to 1,117. And if I do a third time, then remember I'm going to reduce it by another time, and I'm going to have 1,116. And then by the magic of doing this ahead, I ended up with 0.0002 is the probability. So the probability of selecting first not accurate orders and decreasing the pool by 1 and then and the total by 1, and then I'll also do the same thing on the next ones going down. The last problem. It is generally recognized that it is wise to back up a computer. Assume that there is a 3% rate, so here's your probability, of your disk failure in a year. If you store all your computer data on a single hard disk drive, what is the probability that the drive will fail in a year? So remember, this is going to be the 3% of the failure for the year. So my probability that it's going to fail will equal then the 0.03, which is just the 3% written as a decimal, or a 3% failure rate. If all of your computer data is stored on a hard disk drive with a copy stored on a second hard drive, what is the probability that both will fail during the year? So in this case, it's going to be the probability that I'm going to have a fail and another fail, or both fail. So in this case, then I would have the probability of fail, which would be 0.03, but then I'm going to also multiply it times 0.03, and then that would indicate, then that would be then that squared, so it's going to be 0.00, I have 0.9, 1, 2, 3, I think it's actually, I think I've got, let me just double check that one. I think my 0.03 times 0.03 to the -4th, and 9 times e to the -4th is what they have. Okay, 0.03 squared, and so 0.09 to the -4, 1, 2, 3, 4, that would be correct. Okay. The next one, it says if you copy all of your data and store it at 3 independent hard drives, what is the probability that all 3 fail during the year? Now again, we're going to look at the probability that all 3 fail, which again is going to the probability that I have a fail and a fail and a fail. So in other words, I'm just going to take, again, my probability 0.03, but now I'm going to take it times itself 3 times, or 0.003 times 0.03. I think that's signaling that I need to go home because my light went off. And then this indicate 0.03 all to the third power. And by magic, I'm going to end up in 0.123427. Okay, describe the improved reliability that is gained from the backup drive. So with each additional backup drive, the failure rate is diminished. One hard drive would be 3%, 2 hard drives would be 0.09%, and then the third hard drive would be then 0.0027%. In other words, just taking all of these times percents. Okay, good luck. Hopefully you guys can get section 4.2 done, even if it's in the dark.